Okay, so in this video, I just wanted to derive some of the cubic and quadratic quadratic um, functions and see what the symmetry is for them. So in a previous video where I derived the C6v character table, so we figured out these linear functions before in a previous video. And so see that video for that where I derived the C6 character table. We also want to know the rotation vector. But what I want to do here is talk about some of the quadratics. So since you know Z transforms as 1 across the board, the 5 quadratics that are really the most important are those that correspond to the 5D orbital functions. And so Z squared is just going to be, it's like anything times Z is going to be itself. So Z times Z is still Z, transform same symmetry as Z, because it's ones across the board. And the same rule here for XZ and YZ, right? Anything times Z is just itself. So Z times X is XZ and it has same symmetry. So Y, so we know X and Z, the d orbital functions for XZ and YC, these are also what you use in Raman spectroscopy to figure out whether or not you have vibration that is a symmetry allowed. But what other d orbitals are we missing? We're missing xy and x squared minus y squared. So let's start with xy. So we have to now math through this a little bit. We apply, just like we did for x, y, and z in the previous video, we have to think about what happens to each of the operations, one operation in each class for these. xy goes to xy because it's identity. What about C6? Well, we have to think about what happens, right? So when we take a review from last time, when we take an x vector and we do a 60-degree rotation at C6, we're going to be some combination, a linear combination of x and y. So x and y are going to transform together, and this is going to be described by a 2 pi over 6, pi over 3, minus sine 2 pi over 6, sine 2 pi over 6, and cosine 2 pi over 6. That is our rotation matrix. Okay? And so what this tells us is, if we keep this general here, xy, well, x goes into cosine pi over 3, I'm going to use now. X, just 2 divided by 6 is 3, so I simplify 2 pi over 6 to pi over 3. Cosine pi over 3x minus sine pi over 3y. That's the x part of xy. Now the y part of xy is sine 2 pi over 6x plus cosine 2 pi over 6y. And so now we have to factor this out. And so we're going to get cosine. Oops, I'm sorry. I should have kept this pi over 3 just to be consistent. What I wrote wasn't wrong, but just to make this easier, we'll make it pi over 3's, right? So we have cosine pi over 3 times sine pi over 3, and that's our x squared term. Our y squared term is going to look very similar, cos, but it's a minus cosine pi over 3 times sine pi over 3 y squared. And then we have our other terms, which are our xy terms. So we're going to have minus sine squared pi over 3 times xy, these inner terms multiply, and then the outer terms, plus cosine squared pi over 3. What happened there? That's just a funky looking 3. Let's try to clarify that. Cosine squared pi over 3 xy. That was this term times this term. Let's do some factoring here. Let's factor out an xy. And what's going to happen there? We're going to get cosine squared pi over 3 minus sine squared pi over 3 times xy. Okay, and then we're going to get cosine pi over 3 for the other part times sine pi over 3 times x squared minus y squared. Factor that out. Okay, and so we can clean this up a little bit more by taking advantage of a trigonometric relationship, which is cosine of x minus sine squared, cosine squared of x minus sine squared of x equals cosine 2x. Might remember that one from something. And so what this tells us is that this term here is actually cosine, can be simplified to cosine 2 pi over 3 times xy, right? And then we have this other part. Times x squared minus y squared. Now looking at this function, we start with xy, and we got something that's a linear combination of xy and x squared minus y squared. What does this mean? It means that xy and x squared minus y squared are transforming together. And so when we go to the identity, just like how x and y transformed together in the previous video where I derived this character table, you cannot describe how x transforms in C6v space without also taking into account y, right? You have to do it in terms of x and y. The same thing with y, to do it in terms of x and y. Same thing with xy. xy can only be described in terms of a linear combination of xy and x squared minus y squared. Those functions transform together. So when we go to look for the character under the identity for xy and xy minus y together, we have to do a 2 by 2 identity matrix where we keep these together. And then we simply take the trace of the matrix and we get character of this matrix for the identity operation equals 1 plus 1, which equals 2. So we're either going to be one of these. We're either transforming these functions or either transforming as E1 or E2. So let's keep cranking through this and see which one it is. Now we have xy in terms of xy and x squared minus y squared, but we know xy transforms together with x squared minus y squared. So we have to figure out how x squared minus y squared transforms when we do a C6 operation. Okay, well, we know what x does. It was this first term here. So we're going to take that term and write it down. I'm not going to actually write it down. We're going to take that term and square it. So it's this term squared. So I'm going to write that. So we have to envision this, factoring out this FOIL. So we're going to get first term. It's going to be cosine squared pi over 3 x squared. Next term, if we times these two terms, plus sine squared pi over 3 y squared. And then we're going to have two terms that are the same. It's going to be minus 2 cosine pi over 3, because we have two of them that are the same. That's where the 2 comes from. When we FOIL this out, sine pi over 3 x y. Okay, and then we have to minus a y squared. So we're going to take this term, which is y, right? It came from this matrix as a reminder. And we're going to be squaring this, and remember we have to add negative signs because it's minus y squared. So our first term is going to be minus sine squared pi over 3 x squared. Then a minus, because again we're minusing everything, cosine squared pi over 3 and a y squared. And then we have the cross terms, which we're going to have two of them. It's a minus, and those end up being actually the same as this term. 2 cosine pi over 3 times sine pi over 3 times x, y. Now let's simplify this. And so I'm going to combine the x squared terms. X squared terms, you get a cosine squared pi over 3 and a sine minus a sine squared pi over 3. Up, that's cosine squared x minus sine squared x equals cosine 2x. So I can simplify that as just being cosine 2 pi over 3 x squared. Very similar thing with the y squared. The y squared is going to be sine squared pi over 3 minus cosine squared pi over 3. Well, sine squared minus cosine squared is the negative of this. So if we had the negative of this whole thing, that would be positive sine squared x minus positive sine squared minus the cosine squared term. That's what we have with our y squared components. So this is going to get us a minus cosine 2x, which is 2 pi over 3. 2 pi over 3 y squared. Okay? And then we have this 4 cosine, we can combine these terms. Pi over 3 sine pi over 3 x, y. Well, we can factor this out further to now factor out an x squared minus y squared. And leaving this last term untouched. So again, we figured out now that x squared minus y squared goes to a linear combination of x squared minus y squared and xy. That's what we expect. We did the math right. Why don't we do a C6 operation? So now we can write, I'm going to write it up here, maybe in green, our matrix. Oh, I guess I did blue. That's fine. It takes x, y, and really the only components of this that matter are the on-diagonal components. Those are the ones that are going to contribute to the character of the matrix. So what are the on-diagonal components? And just out of habit, I've done x, y so many times. This is not what we're calculating here. We're asking what x, y, there's green. That looks weird. Let's go to blue. We're asking what x, y, and x squared minus y, how do those transform? So if we look at x, y, again, we only care about the on-diagonal components because the on-diagonal components, remember when you take the trace of the matrix, those are the ones that contribute to the character, not the off-diagonal ones. So the on-diagonal components is the coefficient in front of the function that you look at. So x, y went into what? Cosine 2 pi over 3 xy. So we can put a cosine 2 pi over 3 there. And what about down here? Getting ahead of myself. X squared minus y squared. Again, the on-diagonal component is just the component that went into itself. And when we do this matrix, that's also cosine 2 pi over 3. Right? And so when we take the trace of this matrix, what do we get? We get that the chi for this transformation is going to be equal to cosine 2 pi over 3 plus cosine 2 pi over 3, which is 2 cosine 2 pi over 3. Cosine 2 pi over 3, that's 120-degree rotation. That's a -1/2. That equals a -1. And we can already now say that, we have a -1 here. So we're going to be xy, and x squared minus y squared are going to transform together as E2. We proved that. But if you really want to prove it entirely, you'll have to go further. And so I want to do that with you now. And don't worry, you don't have to redo all this crazy math. We can just generalize this rotation for C3 and C2, and then we'll have to do sigma B and sigma D, but those are much easier. Okay, so how are we going to do that? I'm going to erase this for now. Well, think about if we change this to the C3, right? We're trying to figure out the character over here and prove that's a -1. All this math is going to stay the same, except now you're going to have 2 pi over 3. So that's what you're rotating by, not pi over 3, which was for C6. Do twice that much, 2 pi over 3 for C3. And all this is going to stay the same, all this is going to stay the same, blah, blah, blah. But now we're going to have 4 pi over 3 here. And I erased it all. Not to worry, that was by accident. But we're going to keep going here. We're just trying to find here. So what that function ended up being, actually, this, oops, is going to be save us some space here. Maybe it'll be less cluttered. This is our character table. And so that function ended up being, hey, if we rotate it by pi over 3, we got cosine 2 pi over 3 and cosine 2 pi over 3. So it ended up being actually cosine 2 theta, right? It came from that cosine squared x minus sine squared x equals cosine 2 theta. That's where it all came from. But our generic character for rotation is just going to be, generically for Cn is going to be 2. Why did I put sine here? I meant to put cosine. 2 cosine 2 theta. We took the trace along this diagonal, right? We added them. So for C6, equal to cosine 2 pi over 3, which equals -1. For C3, it equals 2 cosine 4 pi over 3, right? Because theta here is 2 pi over 3. We're rotating by. And cosine 4 pi over 3 is now you're at 240 degrees. That puts you to the bottom left quadrant of your unit circle. That's a -1/2. So 2 times -1/2 is -1. And that's what we got. Okay, that was a -1. What if we did, we could generalize this even further. Okay, 3 pi over 3, well, that just equals pi. That's a C2 rotation, 180-degree rotation, right? So using our generic formula here, pi for C2 is just going to be equal to 2 cosine 2 pi. Well, cosine of 2 pi is 1. So we're going to get a 2 here. And lo and behold, we get a 2 here. Now, what about the sigma d's? The sigma v's? Last one, or second to last one here, penultimate one is v, sigma v. So I'm going to draw our x vector. We have to go back to x and y vectors here. And think about our sigma v that we're defining in the first video. We defined one of our sigma v's as going along the x-axis. So it contains the x-axis. That meant that x went to x. And what did it mean about the y? Well, y is looking at itself in the mirror, so y went to -y. And so now you have to go through and say, well, xy is going to go to, that was a sloppy y. xy goes to the x times -y, which equals -xy. And x squared minus y squared, we know xy and x squared minus y squared transform together, goes to x squared, x went to x, minus quantity negative y, because y went to negative y squared, which just equals x squared minus y squared. So your trace of your matrix here, or your matrix that explains this transformation for sigma v, is going to be the matrix that takes xy into negative xy and x squared minus y squared into itself. That is -1, 0, 0, -1. Take the trace of this matrix. Sorry, there should be a positive one here, right? X squared squared itself. Take the trace of this matrix, sum across the diagonals, and get 0. And lo and behold, we got a 0 there. So we're proving that x squared minus y squared and xy transform as E2. Last one is sigma d. Sigma d bisects the x and the y. That's the way we defined it. So x and y are looking at each other in the mirror. So x goes to y and y goes to x. Well, look at what happens there. There, if that's true, then xy goes to yx, which is equal to xy. But x squared minus y squared goes, this is for sigma d, x squared minus y squared goes to y squared minus x, which is equal to negative quantity x squared minus y squared. So x squared minus y squared went to the negative of itself. So for sigma d, x squared minus y squared goes to very similar thing, but now +1, 0, 0, -1, and that gets us x, y, and y squared minus x squared, or negative quantity of it. Same thing, we take the trace across the matrix, so chi of sigma d operation is equal to 1 plus -1, which equals to 0. And look, we got a 0. So that proves that x squared minus y squared, now in totality, we've proven it, goes as E2. What about these cubic functions? Some of these cubic functions are quite easy. Any of the ones that contain z. Remember, z is just 1 across the board, so you can get these. For example, x, y, z, we could easily predict this. And z times quantity x squared minus y squared are both going to transform the same way as this, because there's just this function times by z. Okay, z squared times x. Well, z squared transforms as the same as z, which is all 1s across the board. So you could take z squared and times it by x and y, and that's how you got these ones. Okay, now obviously these ones, these cubics are more complicated. Z cubed, zz. These ones are more complicated, right? Because you'll have to do this same sort of math that we did in this video for these two, but it's going to be, even wilder math, but it's all doable, and you could prove it if for some reason you